Good morning, guys. So today what we're going to do, we're going to start with a new unit for geometry. So what we're going to start working with is we're going to start working with something called transformations. And I think you guys have actually done this already in elementary school. There are 4 different types of transformations that we deal with, 3 of which I think you guys have all already worked with, 1 of them that you guys may not have worked with. So the 4 that we're talking about is translations, right? Translations. We have a reflection, right? We have a rotation. And then we have something that's called a dilation, right? Yeah, we have those 4 right there. And then when it comes to these 4, translations, again, all 4 of these are transformations, because what a transformation is, it's just a different way of moving a figure around, a geometric figure, anything. Whether you're translating, reflecting it, rotating, or dilating, it's a way of moving it around, right? So when it comes to a translation, another word for translation is a slide, right? When it comes to a reflection, another word for reflection is a flip. For a rotation, another word is a turn. And then when it comes to a dilation, dilation is the only one that's different from everything else, because when you dilate a figure, it either gets bigger or it gets smaller. It's the only one that actually changes size. Everything else, the size stays exactly the same. When it comes to translation, reflection, rotation, all 3 of these stay exactly the same size. But a dilation does get bigger, it does get smaller. We'll go over that too then, okay? But going over all these, we're going to go over them one by one just so you can see them. But again, transformations, guys, they're just different ways of moving figures around. And these 4 would be considered the 4 types of transformations, right? So now, just so you guys actually see what it is, right? So when it comes to a translation, and another word for translation would be a slide, right? When it comes to a translation, so we have a graph, right? And whenever we have a graph, it's something that you guys are used to seeing, right? Whenever we have this would be our x-axis, this one would be our y-axis. All the translation is let's say that you have I'll just draw a triangle just because it's the easiest figure to work with. All the translation is, again, it's just a slide. So imagine having this triangle here. All you're going to do is literally slide it around, right? Whenever it comes to this triangle, you just slide it around. It doesn't turn around, all of that. You literally just take it, slide it around. That's all the translation is. So imagine having it like this, where again, when it comes to all of these, they all stay the same size. Just sorry if my figures don't look like it, but all it is when it comes to a translation, you take that triangle, just slide it around, right? Take this triangle, slide it around. And then we'll go more into what actually represents what, which one's the first one, which one's the last one, all of that. We'll go over it. But right now, all I want to show you guys is just all these different ones, right? So that was a translation, right? And then after a translation, we're going to have a reflection, right? So again, another word for reflection would be a flip, right? When we have a reflection, another word for reflection would be a flip. And so again, whenever we're working with reflections, you're going to take the triangle again, or any figure, just in this case we're working with a triangle. You're going to take a figure, and now what it is when you have a reflection, almost look at it as this. You have this triangle, and then focus on where my thumb is. Whenever you reflect something, you flip it, right? You can flip it one way, you can flip it another way. I'm going to flip it over the x-axis, and we're going to go over these in future lessons because we are going to go over them individually, so we can go more in depth into it. But what a reflection is, you take a figure, my thumb, and then you actually flip it. So as opposed to my thumb pointing up, where that is right there, instead of my finger pointing up, when you flip it, now it's going to be pointing down. So instead of the triangle pointing up, when you flip it, now that triangle points down, right? And again, always under the assumption that the sizes do not change. Both figures are congruent. I'm just sorry that the triangles don't look congruent, but that's all a reflection is. When you take the figure, you flip it, okay? It just turns upside down. You can flip it this way, You can also reflect it, let's say if we had it this way, you can reflect it this way, you know what I mean? So let's say we had a point right there. If you wanted to reflect it, again, size doesn't change, but now instead of the point being there, when you flip it, the point moves here. These are reflections, because these are ways of actually flipping a figure, right? So that's a reflection. After we have a reflection, then we have what's called a rotation, right? And now again, a lot of people know rotations just because they're used to hearing the word in their everyday lives. All a rotation is exactly a turn, right? When you actually rotate a figure, you're turning that figure. Usually people will think of like a wheel when it comes to rotations, which is perfect because when it comes to rotations, that's exactly it. It's the idea of having a wheel that turns, right? So now if we had, again, if we had a triangle, we have a triangle right there. Now what it is exactly that idea. And again, when we have this entire graph, it's one big full turn, right? It's always one big full turn. And then once we go back, it's the way it was. So if this is pointing up, again, it's just turning the figure around, right? So it's actually being seen. So when it comes to that, drawing this here, you would have a triangle that would look like this. Just because instead of this point being here, you've actually now turned it. You've turned that point, and that's all a rotation is. You take a figure and you literally turn it all around as it is. It's being rotated. That's what a rotation is. The last one, and again, none of those translations, reflections, rotations, none of those actually change the size. All of them stay the exact same size. The only one that does change size, it's the only one that's different, is what's called a dilation. Now again, we're going to be working more with dilations today because this is the one we're going to be going into more in depth. All the other ones I did want to just show you guys what they look like. A dilation is the only one that's different because it's the only one that changes size. So let's say that we had a triangle. Let's say we had a triangle that looked like this, right? Now what happens with a dilation is a dilation literally, it will change size. One will be bigger, one will be smaller, do you know what I mean? Sometimes it can get bigger, sometimes it can get smaller. The one thing about a dilation is that it is not congruent. Not congruent. And what I mean by not congruent, it's again, it's not going to be the same. It's not going to be the exact same size. The sizes are going to change. And then going into that, when we're talking about dilations, there is another word. And that other word that I'm referring to is something called an isometry, right? Something called an isometry. And what isometry means is that it stays exactly the same. It stays exactly the same. An isometry stays exactly the same. So again, if we have isometry, it stays congruent, right? They're both going to be the same figure, but they're both going to be the same exact size, right? So if we looked at this, this would not be isometry because they're different sizes. If we were to look at this, for example, this would be isometry. And the reason that this would be isometry is because, again, same figure, same exact size. This here would not be isometry, not isometric is another way that we can refer to it. And the reason that this would not be isometric, it wouldn't be isometry, is because the size changed. So again, when it comes to dilations, you see that. It's the only one that doesn't have isometry. So it doesn't stay the same. Isometry just means the size stays the same. This is not having isometry because it changes size. This is having isometry because it stays the same size, right? So whenever you hear that word isometry, that's just what it means. It means it stays exactly the same, right? It's exactly congruent, same size, same shape, right? But now going back to dilations, because the other important part of this is knowing what came first and what came last, right? So if I'm looking at these figures here, right? And I'm gonna use a different color. We don't know whether it got bigger or smaller because you saw me draw it. But now if you guys were just to see this and trying to figure out what came first and what came last, there's something very important that we see, right? So let's put a point right there. Let's put another point right there. Let's call this A. Let's call this A. And even if I gave you this, while looking at that, you still don't ever know which one came first and which one came last because they both have the same label, right? What we usually use to see whether something came first or last is that. And the way that you would refer to that would be A prime. And what this tells us is that whenever you see the prime always comes last. The one without the prime is the one that comes first all the time. So automatically, if you see the prime, it comes last. It looks like a 1. It's not a 1, but it looks like it. So whenever you see the prime, that comes last. The one without the prime, that comes first. And these have names for it, right? So when you see them, the one that comes first without the prime, we call that the pre-image. And again, it's called a pre-image because it comes first, right? So the one that comes first is the pre-image. If the one that comes first is the pre-image, it means that this one, the one that comes last, is going to be called the image. And that's exactly it. It's an image of the first one, right? So again, any figure, whenever we're looking at what came first or what came last, we look at the one that has the prime. The one with the prime comes last. It comes last. And then the one without the prime comes first, right? So the pre-image comes first, the image comes last. The prime always comes last. So in this case, it's important because it's telling us, since this came last, it got smaller, right? That's all it is. And it's just getting that hang of it, right? So now, if I were to take that, right, and just analyze it a little bit further, if I were to give you, again, two different triangles, right? If I were to give you this, and I were to give you, here, I'll even draw it over here. If I were to give you that, right? Again, different sizes. This one's bigger, this one's smaller, but it's needing to know which one came first and which one came last, right? So if I give you this, again, that's F, we still don't know what happened. But now if I were to put F prime here, again, the prime comes last, which means that this got bigger, right? Because if the prime comes last, and the big one is the last one, it means it got bigger, right? This would be our image, and then this would be our pre-image. Again, the one without the prime always comes first. The one with the prime always comes last. So again, whenever you have the prime, it tells you what comes last. And since this one came last because of the prime, it got bigger. That's the importance of it. And again, same thing. This would not be isometry because one's bigger than the other. So that's all dilations are, guys. It changes size. It's always being able to analyze it and all of that. And then just being able to apply it. The math part's easy, right? Because let's say that I had a dilation, right? Let's say that I had a dilation. And again, just focusing on the dilations. Let's say that I had a coordinate. I'll show you, just to make it a lot easier. Let's say we have this graph right there, right? Again, we have a triangle right here, right? We have another triangle right there, right? And so again, I'm going to show you this way, right? Let's make this A. Let's make this 8 prime, right? So again, since that's 8 prime, it means it got bigger, right? Because the big one came last. Let's say that that coordinate right there, actually no, we want to find that one, right? I'm going to give you this coordinate. Let's say that this coordinate here was, let's say it's 1, 3, right? So we know that the coordinate of A is 1, 3. I'm going to tell you because when it comes to dilations, again, it usually gets bigger, it usually gets smaller. In this case, we saw that it got bigger, right? And I'm going to tell you that it got bigger. It got bigger. It was a dilation with a scale factor of 2, right? So what that means is, again, it's getting bigger. I'm going to move it here just to make it easier to see. Again, all that is, guys, when it comes to a dilation, if you see something like that, dilation with a scale factor of 2, I'm going to draw it over here to the side just for you to have it be better to see. Again, sorry if it does start looking a little bit together and all that, but it's just to make it more accurate for you guys to see, right? This would be A prime, right? So what this means is, again, it's just telling you when it's a dilation of a scale factor of 2. Scale factor just means how much bigger or smaller it's getting, right? In this case, since it's getting bigger, the scale factor is going to be 2. And we're going to go over this when we go into similar figures. But since the scale factor is bigger than the number 1, it gets bigger. When it gets smaller, it's between the numbers 0 and 1. So the scale factor of 2 means it's getting 2 times bigger, right? So whenever you actually want to find the coordinates of any figure, let's say that this coordinate was 1, 3. We know that the scale factor is 2. The way that you would actually find A prime is you take that coordinate and now you multiply everything by 2. Because again, scale factor is 2, everything's getting bigger by 2, right? So we multiply everything, right? This would be times 2, this one would be times 2, right? So now, if we were to do 1 times 2, it would give us 2. If we were to do 3 times 2, it would give us 6. And that's how you actually find the image, right? That's how you find the image of the coordinate there. Because if that's 1, 3, this would end up being 2, 6. Because it just means all these times when the triangle's getting bigger, everything's getting bigger by 2. So it means the coordinates are going to get bigger by 2. And if you were to do it for all of them, you would get something that gets a lot bigger. You know what I mean? That's the idea of like dilation, figuring out the coordinate. I'll do one more, guys. And it's just getting in the habit of seeing it, right? And again, any other questions, guys, we will go over everything in class then. But let's say that I had a coordinate. Let's call it F. Let's say F had a coordinate of -2, 3, right? And then let's say that the dilation had a scale factor of 1/2, right? Now, since it's 1/2, it means it got smaller, right? 1/2 means it got smaller. If I want to find the image, if I want to find F prime now, since the scale factor is 1/2, all it is, it's just, again, you can think of 1/2 of 2, 1/2 of 3, you can do it that way. If you want to change this to a decimal, you can do that way as well. But again, if we look at it, 1/2 of 2 just means you would divide each of these by 2, right? Because it's 1/2 of 2. So divide -2 divided by 2 gives us -1. If you want to do 3 divided by 2, it's going to give us 1.5. And that would be the image of F. Because again, since the scale factor is 1/2, we're taking 1/2 of each number. 1/2 of -2 was -1, 1/2 of 3 was 1.5. And that's how you actually calculate the coordinates of the image when it's undergoing a dilation. You can do it that way, or if you wanted to, again, we know that 1 divided by 2 is going to give us 0.5. So if it helps you, just do times 0.5 and then do times 0.5. It'll give you the same thing. If you multiply -2 times 0.5, it'll give you -1. If you do 3 times 0.5, it'll give you 1.5. And any questions, guys, feel free to ask. Take care.